the chapter 2 notes. The title of the chapter is called Atoms, Molecules, and Ions. Atoms, Molecules, and Ions. There's going to be two main parts of this chapter. One part, which is about the history of discovery of parts of the atom, and the second half of the chapter, which is titled, well, it's about how to name molecules. Some molecules you probably already know the names of, like sodium chloride, but what in the world is calcium carbonate? Or sodium bicarbonate, which is commonly just known as baking soda. What is the chemical formula of sodium bicarbonate? That's what the second half of the chapter, one of the big things of this chapter is. So the two parts, the first part that we're doing right now, which is the history discovery of parts of the atom. So starting back in history, well, I guess it's not, I don't have it right here in the notes, but going back is the idea of an atom. The idea of an atom actually comes from the Greek idea of, I don't know if I'm pronouncing it right, atomos, for something that's indivisible. This Greek philosopher said, hey, what is the smallest thing? If I had a piece of gold and I break in half, each half is still gold. I take that half and break in half, it's still gold. And I break that in half, and 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 in half. Eventually I'll get to a piece that cannot be broken down anymore, that I can still call gold. Whatever that indivisible part, the atomos, the thing that can't be broken apart anymore, that thing will be called, well, that's what we now know as an atom. And so although he couldn't see atoms, that's the idea of where the term the atom came from. And that wasn't challenged, and we still use that term in atom. But the smallest piece that still holds, that still has properties of that substance is still called an atom. What Democritus didn't know was stuff like water is made up of hydrogen and oxygen atoms, H2O. He probably would have said, well, the smallest piece of water that you can still call water is a water atom. Again, this is over 2,000 years ago, so, but just the idea of the smallest piece that still has properties of that substance, atom, that is what Democritus started. Okay, so that didn't change. Nothing about that changed until around 1808. And in 1808, this guy named John Dalton came up with Dalton's atomic theory. Dalton's atomic theory had several parts to it. In the beginning, the initial main thing was the same. Atoms are made up of these extremely tiny particles called atom. And that's, well, what Democritus said anyways. He added a few things. One thing was that all atoms of a given element are identical, having the same size, mass, and chemical properties. Atoms of one element are different from atoms of all other elements. So yes, a gold atom is different from silver, which is different from oxygen, which is different from carbon. He wasn't totally correct in that. He said they're identical, having the same size, mass, and chemical properties. We now know there are things called isotopes, same elements, but different. They have different properties, and they have different mass and different sizes. But again, this is 1808. It was still a big thing. Other things that he added to it were compounds. Compounds are composed of atoms of more than one element. The relative number of atoms of each element in a given compound is always the same. So that's one thing he added to it. And another thing he added, chemical reactions only involve rearrangement of atoms. Atoms are not created nor destroyed in chemical reactions. So these bottom point 2 and point 3 are things that Dalton added to the idea of atoms that Democritus definitely did not say anything about. Let's start with the first one, which is the ratio of these things. What do I mean by the ratio? Where it says the relative number of atoms in number 2 of every element in a given compound is always the same. When we talk about carbon monoxide, the ratio of carbon and oxygen in carbon monoxide is always 1 to 1. 1 oxygen for every 1 carbon. In carbon dioxide, though, there's 2 oxygen atoms for every 1 carbon. The ratio is 2 to 1. They're always nice whole numbers, 1 to 1, 2 to 1, 3 to 1. 3 to 4, 4 to 5, whatever. They're nice whole numbers. You will never have a 1.73 to 2.65. They're always nice whole numbers. It is also now known as the law of multiple proportions, that these proportions are always nice multiples or whole numbers. 2 to 1, 1 to 1, something like that. The other thing that Dalton said, let me go back. In number 3, it says, chemical reactions only involve the rearrangement of atoms. Atoms are not created nor destroyed. So if he had 16 X's and 8 Y's, if I had 16 X's and 8 Y's, or 16 red ones and 8 green ones, after they react, they can rearrange themselves. So for every Y or every green one, there are 2 X's attached to it. At the end, I have a total of 8 molecules with 2 X's and a Y per molecule. 2 red ones for every green one in a molecule. So in a chemical reaction, things combine in these ratios, always whole numbers, 2 to 1 in this case. And they are always, no atoms are created nor destroyed. That's also known as the law of conservation of mass. If I had 16 X's here in the beginning, I will have 16 X's or 16 red ones at the end. I have 8 green ones in the beginning, I'll have 8 green ones at the end. There's no loss in number of atoms. Atoms are not created nor destroyed. And that is definitely true. That is true. The only exceptions to that would be in a nuclear reaction. But again, 1808, Dalton, they did not know much about nuclear. Well, they didn't know. I'm not sure they knew anything about nuclear reactions. So, but in general, number of atoms are not created nor destroyed. They can be rearranged. You can break apart bonds, make new bonds. That's a chemical reaction. And that's what that's part of Dalton's atomic theory. Okay, going on to the next thing. Cathode rays. I'm trying to put my face where I'm not blocking the picture. Okay, cathode ray tube. The cathode ray tube was what this guy named J.J. Thomson used to measure the mass per charge of something. Let me actually go to the next slide and I'll come right back to this. So this is a picture of a cathode ray tube. Was a cathode ray basically a tube of low pressure gas? And it actually doesn't matter what kind of gas. It could be nitrogen, it could be neon, it could be argon, any type of gas. So if you have a low pressure tube gas and there's electric current through it, what they see, as you can kind of see, there is a beam of light in it. And they knew this since the early mid 1800s, but they didn't know what in the world that light was. That thing is called a cathode ray. They did know, hey, if you take a magnet, you can deflect or attract that ray, but they still didn't exactly know what in the world made up that ray. In one of the readings, one of the things you have to do is a CK12. You'll see that they found that these things actually have mass. These particles, whatever that beam of light is, they have mass. How in the world did they have determined that thing has mass? They put something like a pinwheel. You know, a pinwheel, something that if you blow on, it starts spinning like a windmill. They put a pinwheel inside of it, and when they turn it on, the electricity, that pinwheel would start spinning. And why would it spin? That's if you had a windmill or you had something, you blow on it, when particles hit it, particles that have mass hits it, it causes that pinwheel or that thing to start spinning. So when they did that, they found, hey, the cathode ray tubes, whatever those particles are, they have mass. Let me go back. Another thing J.J. Thomson figured out was not only did it have mass, when he had this cathode ray on, and there are no plates, no positive and negative plates, there's no north-south, no magnetic fields in there. When there was the cathode ray was just turned on, all the particles would hit point B on a screen. So they went straight across. But when he had 2 plates on there, a positive and negative plate, he noticed that these particles, whatever they were, and again, he did this experiment, I believe, in the late 1800s, 1890s. You don't need to know the years of this stuff. I know it says here he won a 1906 Nobel Prize in physics for it, but he actually did the experiment in the 1890s, and then he was later on awarded the Nobel Prize in physics. Okay, but so he's trying to figure out, okay, what are these particles? One thing he found were these particles were attracted to positively charged plates, or you could say repelled by negatively charged plates. So how do you know that? Because when he had charged plates near there, these particles landed at pretty much point C, not A, C. So if they landed at C, that means these particles are attracted to positive charges or a positive plate. These particles had a overall net charge they had a negative charge, because opposite charges attract. If they're attracted to positive things, then these particles must be negative. If it landed at point 8, however, that would mean that those particles were positive, because it would be attracted to negative plates. So they landed at a lower point, point C, so he knew they were negatively charged. He did not know the actual charge of this stuff, but he figured out the mass per charge of the molecules based on the distance between points B and C. Why? Because the lighter they were, the greater the distance this particle would be deflected by. The heavier it was, the less it would be deflected. Example: imagine you were at you had a shopping cart full of groceries. There's heavy things. There's water bottles in it in a shopping cart. You had another shopping cart that was same size but much lighter. There's only light things in it. You push both shopping carts in a grocery store equally hard. Which shopping cart would go further away? Which one would go not as far? Well, as you probably would, you don't need to know physics and the calculations of it, but the lighter particle or the lighter shopping cart would go further away, and the heavier shopping cart would go not as far. So based on the mass, he did not know the mass. Based on the distance between point B and C, how much they got deflected, J.J. Thomson calculated the mass per charged electron. He did not know the actual mass, he did not know the actual charge, but he did the relationship between mass and charge. So that's what J.J. Thomson figured out. But from that, there's actually another important point. He also found that based on that, these particles in this cathode ray tube were really, really light. And they were much lighter than hydrogen. And you're like, so what? So they're lighter than hydrogen. Well, the periodic table with all the elements were already known. Well, not all the elements, but a lot of the elements that we know now, many of them were already known by around 1900. And so he found that this thing was lighter than hydrogen. Hydrogen is element number 1. It is the lightest element on the periodic table. How in the world could you have something which is negatively charged and be lighter or smaller than an atom? So maybe atoms are not the smallest things. And so, of course, you could kind of figure out what J.J. Thomson is credited with discovering. Something that's smaller than an atom, smaller than the smallest atom known at the time, and is negatively charged. J.J. Thomson is credited with discovering the electron. So that's what J.J. Thomson discovery found out. He's credited with discovering the electron, a negatively charged particle that's smaller than the smallest known atom at the time. He technically found the mass per charged electron. For this experiment, which was again in the 1890s, you don't need to know the actual years, he won the 1906 Nobel Prize in Physics. Going on to another experiment. Robert Millikan's experiment. Robert's Millikan experiment was, I don't know what year this was, in, I believe, actually I'm not really sure, the actual year of this experiment. I want to say 1920s, 10s, but it probably says in a book, but, about more than 100 years ago. Okay, so Robert Millikan's experiment, which he won a Nobel Prize for, measured the mass of an electron. He didn't just take an electron and weigh it. Okay, you don't say, okay, I want to weigh myself, step on a scale. That's what I would do if I want to weigh or determine my mass. However, an electron, even today, it's so light, You can't just take an electron. You can't take tweezers and pick off an electron, put on a scale. One, you can't. The electrons are way too tiny for that. And two, there are no scales that will measure just the weight of an electron, especially not, over 100 years ago. So how did he do that? He ionized a whole bunch of oil droplets. And you'll read a CK12 thing about how he did that. But he used X-rays to ionize these oil droplets. And one of these oil droplets would fall down a very, very, very tiny hole. These oil droplets, he knew how many drops of oils were in or the size of this thing, and he could also see it in his viewing microscope. But let's just say for the point of this exercise that there were 1,000 atoms in that oil drop. And each one of them were charged with an extra electron. So we're talking about extra 1,000 electrons. I'm using these numbers as just for nice number's sake. Well, this oil drop, based on gravity, would fall. And we know the force of gravity. We know how to calculate that and how fast it should fall. But since these oil drops were negatively charged and he had a negative plate here, he could change the dial of this charged plate. Electrons on here and a negative charge plate would repel. And if he turned it on too high, this negatively charged plate that is, this oil drop would go back to the top. It would repel, it will actually want to get away. If he turned it down too low, gravity would take hold and pull it straight down. But if he can turn the dial just right, such that this thing appears to be floating in space, and again, he's viewing it through a microscope. That's when the force of gravity pulling all those electrons down, and the oil drops, the mass of the oil plus those electrons, is equal to the charge of the plate pushing it back up. Based on that, he could calculate the charge of one electron. Well, he found it for 1,000 divided by, assuming there's 1,000 electrons there, divide by 1,000, you can find the charge of one electron. The charge of electrons are measured in something called a coulomb. Just call it charge for now. We're not going to use the SI units for this of coulomb. I'm just going to call it charge, but technically it's a coulomb. Negatively charged because electrons are negative. Well, if I went back to J.J. Thomson experiment, I said he found the charge per mass of an electron. Here was the actual number that J.J. Thomson found. Minus 1.76 times 10 to the 8th coulombs per gram. If I know the charge, I know charge per gram. This is like a conversion factor. 1 gram of this stuff has a charge of 1.76 times 10 to minus 8, to the positive 8 charges. If I know this conversion factor, I know the charges, I can therefore calculate the mass of an electron. So this thing here from J.J. Thomson was a conversion factor. Robert Millikan's experiment found the charged electron. We use Thomson's charge per mass of electron to calculate the mass of electron. And Millikan's experiment to calculate the mass of electron was actually within about 1% of reality. So of the actual, what I mean by reality is that even though this experiment using oil drops, X-rays, and a viewing microscope, his numbers were really accurate, relatively speaking, within 1% of what we know now with much better equipment than in the 1900s. Okay, so that's Robert Millikan's experiment. Okay, so I'm going on to, actually, I'm going to skip the slide for now. I'm coming right back. So they, back then, so they know there are negatively charged particles called electrons, discovered by J.J. Thomson. So J.J. Thomson discovered the electron, or he's credited for discovering the electron, won a Nobel Prize in physics for this thing. And they kind of determine, okay, so atoms aren't the smallest thing. There's these electrons, these negative things. Okay, well, they knew if there's negative, there has to be something positive to balance it out. So they kind of asked, like, well, Nobel Prize winning scientists, J.J. Thomson, so what does an atom look like then? And he didn't know. He hypothesized that, well, these electrons are there. We know that. He discovered them. These electrons must be stuck in a positive pudding-like stuff. And he knew because if there's negative, there has to be positive. These negative things are stuck in a positive-like pudding. It was called the plum pudding model. I have never had plum pudding in my life. I've never even seen plum pudding. I know what pudding is. And I assume what he meant was there's these like negative plums stuck in a pudding. You know, that kind of, and a pudding's positive. These negative things, electrons, are stuck in it. And that was the idea, that model of the atom. And that idea stuck around until until it was disproved. We know that model is not correct, but again, in, say, 1900, when they discovered the electron, I mean, who's going to argue? Unless you have evidence that Thomson's wrong, well, I mean, sure, I'll believe the Nobel Prize-winning scientist who just discovered the electron. I don't have any proof otherwise. It wasn't until, I believe it was 1906, when this guy named Rutherford, I think his first name is Ernest Rutherford, and that's a slide after this, and his experiments to discover that this model, called the plum pudding model, was incorrect. But before I go to Ernest Rutherford's model, I need to explain something that he used, which was, he used something called alpha particles in an experiment. So I want to explain what alpha particles were. Again, this is around I think the year was 1906. In 1906, this guy named Ernest Rutherford, he borrowed some uranium, I don't know what uranium oxide, but he had some uranium product. Oh, it even says down here, uranium compound. I believe he borrowed some uranium oxide from his friend and fellow Nobel laureate Marie Curie in France. Ernest Rutherford is in Edinburgh. I don't know if that's Scotland or England, but one of those. So he borrowed some uranium from her. And they knew at the time, they didn't know what it was, but uranium products or radioactive substances gave off three types of particles: alpha particles, beta, and another one, gamma, which is just like A, B, C, the first three letters of the Greek alphabet. So it's not that original. Alpha, beta, and gamma. Alpha particles were attracted to negative plates. Beta particles are attracted to positive plates. Gamma, neither. It just went straight through. I'm going to talk about alpha right now because Rutherford used alpha particles. You don't need to know what they actually are. In fact, in 1906, they had no idea what in the world it is. We now know what it is. They are helium-4 nuclei. But again, you don't need to know what it is. What they did know in 1906 was these alpha particles were highly, highly energetic. Lots of energy. Secondly, because it's attracted to negative plates, these alpha particles must be positive. So what they knew, high energy and positively charged. That's pretty much what they knew about it. Again, they didn't know much, but they knew it was positively charged and high energy. Okay, so Rutherford took some uranium compound. Let me get to the slide I want to use here. So you had the alpha particle emitter. He fired at a very, very thin piece of gold foil. And Ernest Rutherford's experiment won him the 1908 Nobel Prize. This experiment was in 1906. You don't need to know the years again. So he took some alpha particles. He fired a piece of gold foil that was really, really, really thin. I'm talking about maybe, I think they said it's around 6 atoms thin. How did they do that? I don't know, but point is he did. So he fired alpha particles at a piece of gold foil, and when he did, what he expected was, of the alpha particles fired, pretty much, every one of them he expected to hit the very back. And they kind of almost did. Okay. In fact, I think the number of alpha particles fired off per minute was around 132,000 alpha particles were emitted per minute, fired, and he put the detector back, and he saw 132,000 alpha particles hit in the back per minute, which didn't surprise him. What surprised him was he actually put that alpha particle reader all along the side, all around it. He actually made a student of his who made this detector. His name was Geiger, okay, the inventor of the Geiger counter. And another guy, another undergrad, his last name is Marsden. I don't even know his first name. He made him, says, okay, let's see if there's any other alpha particles all around it. And so, which is just shown as a detecting screen. But so you put the alpha particle detector right here, or in the back, or in the front. And when he put it on the side or in the back, they notice, hey, there's a few alpha particles. Not much, not 132,000 per minute. Maybe 5, 10, well, actually more than that, like 10, 20 alpha particles per minute. And same here, they're like, oh, that's just from the background, who knows where it's coming from. And just to make sure it's from the background, if we just remove the gold foil, so this is now gone, there shouldn't be any reading. And when they removed the gold foil, there was nothing on the detector. They put the gold foil back, it was back in the detected alpha particles. Not on the very back, but on the side again. And also here, and on the front, all around it. So they said, maybe something weird with gold. Let's try it with platinum foil. Let's try different types of foils. They tried all different substances, and they found the same thing. So what did that mean to Ernest Rutherford? What that meant to Ernest Rutherford, again, alpha particles were positively charged high energy. So what they figured out was, there's something inside the gold atoms. Don't know what. Okay. Again, this is 1906. Don't know what. But it will hit something that is also positively charged and cause the alpha particles to either bounce back or at least deflect or reflect, one or the other. But since about 132 alpha particles per minute comes out and about 132 alpha particles per minute hit the very back, atoms are mostly empty space. That's one of the first things he said. Alpha particles are mostly empty space. But once in a while, an alpha particle hits something that is very massive and is also positively charged, because alpha particles are positively charged. Hit something positively charged and cause the alpha particles to deflect or reflect back. He said, I don't know what the thing is. I know it's something big inside or something massive. Massive does not necessarily mean big. Most of the atoms empty space, but there's something inside the atom. And since the center of a cell was called a nucleus, he also called that thing, the center of the atom, the nucleus. Since the atoms have a positive charge and it's concentrated nucleus. This is the opposite of J.J. Thomson's plum pudding model. Remember, J.J. Thomson's plum pudding model said that, hey, these electrons are all stuck in a positive pudding. Well, that's not true. That positive charge is stuck somewhere in the center. And from that, we now know that plum pudding model is incorrect. So Ernest Rutherford's experiment won him a Nobel Prize in chemistry. We also do the same experiment. We now know, well, they didn't use alpha particles. They used, I don't know what, something else. And they fired it into protons, into neutrons. And they found that protons are made up of even smaller things. Neutrons are made up of even smaller things. These smaller things we call quarks. You don't need to know that, but the idea of how it's been determined was almost exactly the same as Rutherford's experiment using alpha particles. That they saw that, hey, some stuff deflected or reflected back. There's something inside the nucleus. There's something inside the protons. Okay. Part 2 and number 2 and 3 were not discovered by Rutherford, but we now know what is that positive charge. The positive charge was caused by the proton, which is the opposite charge of the electron. The mass of the proton is 1,840 times the mass of the electron. Again, Rutherford did not discover point 2 and 3. He found that, just part 1, that there's a positive charge in an atom, which he called the nucleus. He also determined the size of the nucleus. He also found the size of the nucleus. So how in the world did he determine the size of the nucleus? Well, if this is an atom, and that's a dot, or the nucleus. If I said, hey, you can't, but throw darts at, the screen, and there's a dot in it. the chances of you hitting that dot, not very high, primarily because that dot's really tiny. If the dot in the center were bigger, the chances of you hitting it would be much greater. If the dot was even smaller, your chances are much smaller. Well, based on the number of alpha particles that got deflected or reflected, he used that to calculate the size of the nucleus based on how many alpha particles should have reflected back. From that, he calculated since we knew the radius is about 100 picometers, or 1 times 10 to the 10th meters, and based on the number of alpha particles deflected or reflected back, he calculated the nucleus had a radius of about 5 times 10 to the minus 3 picometers. That is order of magnitude about 5 times smaller, 10 to the 5th time smaller. That's a huge difference. What is that the scale of? That's kind of like saying if an atom is the size of the Houston Astrodome. If you don't know what the Houston Astrodome is a giant football stadium. Imagine like the LA Coliseum, a very big football stadium. If an atom was a giant football stadium, then the nucleus is a marble on the 50-yard line. So that's the same scale. So that's why we said the atoms are mostly empty space. Alpha particles going through the atom will mostly go straight through. But once in a while, one of these alpha particles, especially if you're firing 132,000 per minute at the atom, once in a while, one of these alpha particles will actually hit the nucleus and cause it to deflect back or reflect back. So that's how he calculated the radius of the nucleus, or nuclear radius. This 100 picometers, by the way, is a good number to know. You don't really need to know it for this chapter, but that's around the size of a typical atom. About 100 picometers, or 1 times 10 to minus 10 meters. Okay, next thing. Chadwick's experiment, 1932. I think this is one of the last experiments. So we discovered the electron, J.J. Thomson. They discovered the nucleus, a positively charged nucleus, which later on they also discovered the proton. Not this experiment though. But there was a problem that wasn't discovered until 1932. Hydrogen is element number 1, they knew, had 1 proton. Helium was element number 2, had 2 protons. It has double the number of protons as hydrogen. So you would think the mass of helium to hydrogen, since it has double the mass, should be double, or 2. However, the measured mass of helium atoms compared to the mass of hydrogen atoms was 4 times bigger, not double. So there's this extra weight in atoms that were like, wait, atoms are protons, which they actually discovered, I believe, by 1930, and they're made up of electrons. Now, why is there this extra weight? Where in the world is this extra weight coming from? Well, I don't know why Chadwick was firing alpha particles at beryllium, but he did. And when he did that, it converted beryllium into a different element, carbon. Lots of energy because it's a type of nuclear reaction. And it gave off another particle that had mass but no charge. And that was the missing mass in atoms. That they couldn't figure out, wait, there's all this extra weight in atoms, but it's not positive or negative. He just finally discovered this uncharged particle that had the weight of about a proton. Okay? He found an uncharged particle that had about the weight of a proton. That, of course, is the neutron. The neutron, which is neutral, meaning no charge, has the mass of approximately that of a proton, 1.67 times 10 to the minus 24 grams. You don't need to know the actual weight of these things. But the proton, neutron, about the same weight. They're not exactly equal. In fact, here's a slide with the numbers, actual numbers. This is table 2.1 in the textbook. Notice proton, neutron, 1.672, 1.674. Not exactly equal, but very, very close. Okay? Proton, neutron weigh about the same. So even though it says they're equal here, not exactly, but we will say more or less they weigh about the same. and it takes 1,840 electrons, equal to weight of a proton or neutron. So this part in red, you should know proton and neutron weigh about the same, though not technically the same, is less than 1% off. And it takes 1,840 electrons to equal to the weight of the proton and neutron. Okay. So you should also know, you don't need to know the Coulomb charge, but you should know electrons are negative, protons are positive, and neutrons are neutral. Okay. So we have our different parts of the atom. We have discovery of the electron by J.J. Thomson. You have the nucleus discovered by Ernest Rutherford. We have the neutron discovered by Chadwick. Now let's talk about how do we write atoms, okay? And different numbers involved with talking about atoms. There are two numbers that we use to talk about atoms. One is atomic number. The symbol atomic number is Z. You would think it's A, but it's not. A stands for something called mass number. I'll get to that. Atomic number is the number of protons in a nucleus. That is how our current periodic table is currently organized. It's organized by the number of protons in a nucleus. And so that is Z, the number of protons in a nucleus. Next thing, the mass number. Number of protons plus neutrons. Protons plus neutrons is the mass number. Or number of protons being Z, it's the atomic number plus the number of neutrons. Term isotopes, atoms of same element, but different number of neutrons in a nuclei are isotopes. Let's just give you, before I give you examples, how we usually write these symbols is this. We have the element symbol X, whatever, that could be carbon, that could be hydrogen, it could be uranium, whatever element we're talking about, just put X right now. And on the top left, we have the mass number, underneath is atomic number. On top is the mass number, underneath is atomic number. On top is the mass number, underneath is atomic number. On top is the mass number, underneath is atomic number. On top is the mass number, underneath is atomic number. On top is the mass number, underneath is atomic number. Mass number is on top, atomic number on bottom. Mass number is on top, atomic number is on bottom. Mass numbers on top, atomic numbers on bottom. Okay, here you can probably see hydrogen. Mass number 1, atomic number 1. Hydrogen. Atomic mass number 2, atomic number 2. Number 1. Sorry. Mass number, top number is mass number, bottom number is atomic number. This is also called hydrogen 3, mass number 3, atomic number 1. So when I name these things, I actually call it based on the mass number. This is called hydrogen 1. This is called hydrogen 2. This is called hydrogen 3 when I name this stuff. Here, the name of this thing would be uranium 235. The name of this one would be uranium 238. So the top number is a mass number, the bottom number is atomic number. Lots of times we actually don't even write the atomic number. Like lots of times I just wouldn't write the 92 or the ones underneath. Why? It's on the periodic table. Uranium is atomic number 92. So sometimes that 92 there's a little bit redundant. We don't need it. But if you write it down, that's fine. So from this, I can also calculate the number of neutrons. Why? The top number is protons plus neutrons. The bottom number is just the number of protons. If I subtract, if there's one proton and neutron total, but one of them's a proton, that means there is no neutrons here. Let me just show you. That's better, easier to see in the slide. If there's one proton, the red ones are one proton, and the top number is total number of protons plus neutrons is still 1, that means there's no neutrons here. Hydrogen 2 has one proton, one neutron. The bottom number of protons 1. The number of neutrons 2 minus 1, or 1 green one. Green representing the number of neutrons. Hydrogen 3 has one proton. Atomic number 1, 1 proton. The number of neutrons 3 minus 1, or 2 neutrons. So if I want to know how many neutrons are in uranium 235 right there, how many neutrons? How many neutrons would it be? It would be 235 minus 92, and I'm not a human calculator. I'm too lazy to think. 235 minus 92, according to my calculator, says it's 143. This thing has 143 neutrons. How many neutrons does uranium-238 have? Well, let me do the math. 238 minus 92. I got 146 on my calculator. There's 146 neutrons in that case. Okay, so to find number of neutrons, subtract the mass number, the top number, minus the atomic number, the bottom number. Okay, if we know isotopes, we can answer questions like this. How many protons, neutrons, electrons are in this? Well, actually, I didn't get to electrons, so sorry, protons and neutrons. Protons, easy. It's the bottom number, 6. Neutrons, 14 minus 6, or 8. And the number of electrons, okay, I didn't say it mentioned here, but if there's no charge, the number of protons equals the number of electrons. Since we have 6 protons, we will have 6 electrons. So 6 protons, 6 electrons, and 14 minus 6 neutrons. Okay, now try answering this question. How many protons, neutrons, electrons are in carbon 11? Again, we always call it based on the top number, carbon 11. Okay, so the answer, 6 protons, 5 neutrons, 6 electrons. 5 neutrons because 11 minus 6 is 5 neutrons. And the number of electrons equals the number of protons. Since there are 6 protons, atomic number 6, there will be 6 electrons. Okay, so our modern periodic table, I'll move my face right in the middle. Okay, so our modern periodic table. Notice here are the green parts. That's actually going to be very important later on. Notice parts of our periodic table. There's this green part. Those are the metals. We have the blue parts over here plus hydrogen. Hydrogen plus this corner of the periodic table are nonmetals. And the in-between, these gray ones, are called the metalloids. If we just cut the periodic table at an angle from this corner, cut it, everything that you cut plus along the cut line, in a way, are the metalloids. They're also known as semi-metals, but this table is called metalloids. You're going to have to know whether an element is a metal, a non-metal, or a metalloid, given just a regular periodic table. Okay, I know this one is colored, so you can tell, but looking at a regular periodic table, you should be able to determine whether an element is a metal, a non-metal, or a metalloid. If you're given the element potassium, I know it's colored on here. You're asked, what is potassium? Metal, non-metal, or metalloid? Well, since it's on this side of the period, on the left side of the periodic table, it's a metal. If you had the element chlorine and you're asked metal, non-metal, or metalloid, you should know it's in this upper right-hand part of the periodic table. The only exception again is hydrogen. But in this upper corner of this periodic table are the nonmetals. And of course, these are in between. Okay, so the periodic table is broken down to 18 groups, okay, and 7 periods. What? Just so you know, periods go left and right. There's 7 of them. 1, 2, 3, 4, 5. Am I counting? 1, 2, 3, 4, 5, 6, 7. Okay, I just couldn't count. Okay, so there's 7 of them. You're like, what about these? These technically actually fit in here. Notice 57, 56, 57. Then down here is 58 through 71. Then 72. So these actually fit in there. And same after 89, 90 to 103, then 104. So these elements like thorium, element number 90, is technically part of period 7. Even though it's put way down there. Okay, so our periods go left and right. Our up and down are our groups. There's 18 groups and 7 periods. You can even see it already numbered, 1, 2, 3. We'll talk about what the A's and B groups are later, not right now, but 1, 2, all the way to 18. So if we're talking about element like aluminum. Aluminum is in group 13. You can see the 13 at the top. It's in group 13. Oh, this happens to be element 13, but group 13 and period 1, 2, 3. Third row, or period 3, group 13 elements. So that's how you can use this periodic table. There are 4 groups on the periodic table that have special names that you have to know them. Group 1, also known as the alkali metals. Group 2, also known as the alkali earth metals. We have group, I forget which one I have first, group 17 and 18 have special names. They're known as the halogens, and group 18, also known as the noble gases. There are 4 groups that have special names. What about group 15? Does it have a special name? No. You call it a nitrogen group if you like. Or just group 15. We'll get to A's. It is group 5A as well. But the nitrogen group does not have a special name. The first 2 and last 2 groups have special names, and you will need to know the special names. Alkali metals, alkali earth metals, group 1, group 2. Halogens, group 17. And noble gases, group 18. Those are special ones you do need to know. Okay, let me move my face again. Okay, so last slide for this part today. Natural abundance of elements on Earth's crust. So the Earth is made up of primarily silicon and oxygen, mostly because rocks are silicates, silicon oxygen molecules. So a piece of granite has lots of quartz, which is just pure silicon dioxide in it. There's other elements, aluminum, iron, calcium, magnesium, and all other elements, only 5.3%. This is the makeup of, if you took all the elements on Earth and you separate them out, this would be the breakup of it. The human body is not the same as the Earth. Here it is. If you took all the elements in the human body and separated it out, you'll see your body's mostly carbon, oxygen, hydrogen, mainly because water, H2O. Just so you know, hydrogen is the lightest element on the periodic table. That's why there's so much more oxygen than hydrogen. This is by weight, by mass. Carbon, 18%. Everything else, well, there it is. So you don't need to know these actual abundances, but just like for your information, what makes up the human body, the elements that make up the human body, as well as the elements on Earth.